All right, chemistry people, we are going to start our lesson today. We are going to do our lesson on the SI system, otherwise known as the metric system here in the United States. Part of what we really need to do before we really dive into the metric system or the SI system is do a little review on scientific notation, because in chemistry, we are going to be using some really big numbers and some really small numbers. And instead of taking the time to have to count all those zeros after a really big number, or maybe before the really small number after the decimal point and see how big that is and maybe miss a zero, it's a lot easier to use scientific notation. So we are going to just do a little review on that first. So let me get my pen out. So scientific notation, here we go. We need to, I do not want these emails to be coming up right now. Okay, we need to do a plug for calculators. Okay, so calculators are a must in this class. If you do not have a scientific calculator yet, please go out and get one. I do have a few in the class that you can borrow if you do not have one. They're on the side counter. I'll show them to you in class if you need one. Okay, remember, you don't have to get an expensive one. Probably the best one I like is a TI 30XIIS. I saw them on sale the other day at Target for $11. I'm sure they're also at Walmart for about the same price. So $11 to $12, maybe $13 is about how much they cost. Anyway, okay, write the following numbers in scientific notation. Okay, so I have 245 million. I don't want to count all those zeros. So basically, I need to take the decimal point from here to here. The whole idea of writing things in scientific notation is I write it in a number that ranges from 1 to 10, and then I have a power of 10 to some exponent above it. This tells me how large or small that number is. So I want to move my decimal point right here. So I'm going to write this as 2.45. And now I need to count how many spaces I moved this decimal. So I moved it 2 spaces here, plus 3 here, plus 3 here. So 3 plus 3 is 6, plus 2 more is 8. And since I had to move that decimal point to the right, to the left, not to the right, to the left, my exponent here is going to be positive. Let's try this at a better 8. So 2.45 times 10 to the 8th would be my thing. Okay, so on B, let's look at this one. This is a rather small number. I'm moving my decimal place here. So I'm moving my decimal place to the right. So I know that my exponent, because I'm moving it to the right, is going to be negative. So anytime I move my decimal place to the right, my exponent is going to be negative. Anytime I move my decimal point to the left, my exponent is going to be positive. So I'm going to do 3.4. And I need to figure out how many spaces I moved it. So 3 plus 3 plus 3, that's 9, plus 2 more is 11. So 3.4 times 10 to the negative 11 is what we are going to be going for. Okay, see if you can try C, D, and E on your own. Pause this video for a second. Okay, you ready? Let's go over these. Okay, so I need to move my decimal place from here all the way over here between the 6 and the 0. Okay, so I'm going to have 6.02 times 10. I move my decimal place to the left. So I know this is going to be a positive exponent. So 2 spaces here, plus 3 is 5, plus 3 more is 8, plus 3 more is 11 plus 3 more is 14 plus 3 more is 17. So 6.02 times 10 to the 17. That's a horrible 7. Okay? Now, you'll notice that we can put this in an exponent or scientific notation. We're only going to move this one place. I'm not really a fan if it's only moving it one place of moving it at all, but if you want practice, here's what we're going to do. We're moving it to the left. So this is going to be 1.00045, and we only moved it one place, so 10 to the 1 here. And on E, we're only going to move it one place to the right. So this would be 1.4 times 10 to the negative 1. Now, I don't think personally that just moving it one place is worth it. I think it's worth just keeping it in normal notation because that's not super hard to read. That's not a lot of zeros. But these others, those are a lot of zeros. So it makes it harder to read. So scientific notation is easier to read when you have a lot of zeros. Okay? So let's get into significance of measurements. Before, you probably just measured and you never really understood why you were reporting the numbers that you were recording. But today we're going to look at why you're recording the numbers that you're recording and what that actually means. So here, I want to record the measurement shown below to the correct number of significant figures. So when we talk about significant figures, it means that the last digit that I record for a measurement is an estimate. Okay, so I'm always going to try and estimate my last digit. So if I look at this paperclip, I see that this paperclip ends right about there. So I know for sure I've got 5 centimeters, but I don't have 6. So I know for sure I've got 5. And these are each tenths or millimeters. So I know for sure I have 1, 2, 3, 4, 5, 6, 7, 8. I know for sure I've got 8, but I don't quite have 9. So I'm pretty sure of that 8. But here in between these two is where it gets tricky. Now, are we like right in between? Are we a little bit closer to the 8 or a little bit closer to the 5? Now, I want to like undo all these marks that I just did. So if I look at this, I am going to go right at the end. I feel like I'm right there in the middle. So I'm going to do right in the middle. There's 10 hundredths of a millimeter in there, or 10 tenths of a millimeter in there. So I'm going to put it right in the middle. That digit is just an estimation. This is my best guess with what my eye tells me. Would I be equally good by writing 5.84? With that being my guess? Yes. Could I be equally as good writing 5.86 with 6 being my best guess? Yeah. That last digit is always going to be an estimation with your last measurement bars that you have, and you're going to be trying to guess in between them. Okay? So when we look at this, we can only estimate that last digit. So how many estimated digits can I include in a measurement? Just one, and it's always the last digit. Okay, so let's do some more practice here. When we look at this diagram, for example, I know for sure I've got 5 centimeters, right? I don't quite have 6. And I know for sure I have 1, 2 millimeters. That I know. But in between that 2 and that 3rd millimeter, I don't really know exactly where it's falling. I think it's closer to the 2 than it is the 3. So I'm going to estimate this as 0.03. That is an estimated digit. Where we don't have markings and we have to guess in between markings, that is where we have to make our estimated digit. And remember, we can only make one estimated digit. So perhaps this is going to help. Notice I have the same measurement, but here I have markings. Here I have no markings. So on the one that has no markings, I know I've got 2 for sure. That I know. But I know it's somewhere in between 2 and 3. But I don't know exactly where. If I just eyeball it, it looks like it's about halfway through. So I'm going to estimate 2.5. That would be a good estimate. But here on this top ruler, I know for sure I've got 2. I know that for sure. And I know I've got 1, 2, 3, 1, 2, 3, 4, 5. I know for sure I've got 5, so I know that digit. And then it's somewhere between the 5 and the 6. Here I have to estimate. Is it right in between? It looks like we estimated, yes, that it was right in the middle. Could I be equally good at saying 2.54 or 2.56? Yes, those would be valid measurements because remember, this last digit is always an estimation. Okay, so you need to be comfortable estimating in between the last measurements that you have. Oh my goodness. Okay, let's go on. So you've probably seen enough rulers and been dealing with rulers for a while. How many of you guys have actually had to measure in what we call a graduated cylinder? So a graduated cylinder, you'll notice that the liquids do not sit evenly in the graduated cylinder. That's because most of the liquids that we try and measure are water-based, and water has this principle called adhesion. You probably remember adhesion from biology. You've talked about it with capillary action and other properties that water has. Now, it has adhesion because it actually is more attracted to the glass of the cylinder than it is to each other. So it will try and climb up the walls of the glass. That's why we have that adhesion going on. So to keep everything uniform when we are measuring glass and water, we measure at the bottom right here. That bottom of this curve is called a meniscus. So we try and measure at the lowest point of where that water is, right there. Okay, so if I look there, I definitely have 4D. And if we look at these lines, there's 10 lines between 40 and 50 so that we know each of these lines are 1. So I have 41, 42, 43, 44. I know for sure I have 44 mils, but it's somewhere between 44 and 45. Now, is it right there in the middle? I'm going to erase things so we can see things a little bit more. I don't think it's right there in the middle. It's a little bit closer to 45 than it is 44. So I'm going to say 44.7. Would I be equally good in saying 44.6 maybe? Or 44.8? Yes, Because remember, this last digit is always an estimate. Okay? So we are always going to have an estimate in our answer when we have to do this. Okay? So your homework tonight is going to be a whole bunch of putting things in scientific notation or taking things out of scientific notation. And then I have a whole bunch of things that I want you to measure and give me an estimate on them. Okay? We're going to wrap up by introducing some of the metric system here. So the metric system is actually French. So Système International de Units, so SI system. Here in the United States, we call it the metric system. Oh, that's a horrible R. Metric system. The rest of the world calls it the Système International, or the international system. By the way, we're the only country in the world that really doesn't use this system. Okay? So we're kind of off on our own here in the United States. And I don't know why the United States continues to want to do that, but I don't get to make the policy decisions. If I did, we would all be using the metric system. Anyway, scientists need to report data that can be reproduced by other scientists because guess what? Other scientists send their papers worldwide and they all want to make sure that it's good so that other people can do it. And when other people can do it, doesn't that reinforce the idea? Yeah. So thus, there is a need for a standard system of measurement. In 1960, an international committee of scientists met up to update this existing metric system. In fact, it was updated just a couple years ago, like in 2015. So I should update that. They redefined a couple of measurements just a couple years ago. The revised system is called the Système International de Units, which is abbreviated SI. There are 7 base units. So here are our base units. Time is in seconds, okay? And we do use seconds here, and we are doing the classic 60 seconds per minute, okay? Length is done with meters. You've seen meter sticks. Length, we are measuring how long something is. Mass is done in kilograms. In chemistry, we will usually use grams. Grams are super, super light. So if I had 1 milliliter of water, that would give me 1 gram, just to give you an idea of that. Amount of substance, we use moles. We will be talking moles later in this year, probably third quarter, maybe second quarter, depending. Electric current, we use amps or amperes. And luminance, we will use, or intensity. This is how bright a light is. In the SI system, we use candela. You will be using these in physics. Physics is where you will see those as well. Okay? Oh, and temperature. We use Kelvin. We also in the SIU system use Celsius. We will be going back and forth between Kelvin and Celsius. Usually we will use Celsius. Okay? We are not usually very familiar with that in the United States because here in the United States we use Fahrenheit. Celsius is a much easier scale to use. So anyway, we will start using these SI units next time. I'll go over them again. And it doesn't have volume on here. So we'll talk about volume a little bit, and we'll start using these SI system, using unit conversions and learning how to convert. All right? Have a great day. We'll talk to you later. Bye.